lesson. I thought we had done it already, but apparently not. And that is configuring static routes. It's not that complicated of a section, but something we should definitely review before we move on to dynamic routing. So does anyone have any questions on the labs or any questions on anything we've done so far? Perfect, thanks, Jeff. If not, then let's take a look at configuring IPv4 addresses and static routes. Over here. So in this particular section, we're going to talk about IP routing, which we've already talked about, so we're not going to do too much there. Looking at connected routes, it says configuring connected routes, but that's just really configuring IP addresses on interfaces. And then configuring static routes. And then we'll talk about how routers will forward packets based on the longest match in the routing table. So we'll take a look at how that's going to work. So we know why we need routing, right? Because we have our local subnet, and we can talk to anything on the local subnet without a router. So as long as it's on the same VLAN or on the same subnet on the same physical switch, we will be able to communicate. If we're not on the same subnet, then we need some method of getting there, and a router is how we're going to do that. So routers are what allows us to connect different routed subnets or broadcast domains together to be able to communicate. Now, they don't pass broadcasts. They only will pass unicast and or multicast addresses depending on how they're configured. So anything that's remote will require routes. And routers will use the routing table in order to determine where a packet has to go. So in this case, we have R1, and we're looking at the internal workings of R1. We have an Ethernet port over here. The Ethernet frames get stripped off, as well as the footer, the trailer gets stripped off as well. And the IP packet is analyzed for the destination IP. It then looks that up in the routing table and determines where it's going to send it. In this case, it's sending it to a serial link using HDLC. So it's going to send it to that interface. It could also be sending to another IP address, a destination IP at the other side of this link. That's a possibility as well. But it uses the routing table to determine that. And then it puts the appropriate layer 2 headers back on, in this case HDLC, and sends it on its merry way out the physical connection. So in the example here, we have multiple subnets, right? We have 1 here, 2, 3, 4, 5 different subnets that we want to be able to route traffic. And our goal is to route traffic from our internal subnet here, 172.16.1, over to 172.16.2 and 172.16.3. These networks in the middle, we're just using to traverse. We're not actually, there's nothing out here to communicate with. So this is what we're going to use for the example. So in this case, host A over here, 172.16.1.9, wants to send to host B over here at 172.16.2.9. So it puts the packet together, the IP packet, with a to address, and Because it's on a different subnet, it knows that it has to send to its gateway. Now, it's not sending to the gateway IP address, it's sending to the gateway MAC address. So in the Ethernet frame, we will see the 2 as the MAC address of the router. In the IP packet, the 2 is still going to be the IP of the destination. So A then looks in its ARP table to see that it has to get that MAC address, right? It looks up 172.16.1.1, its gateway, to say, okay, there's the MAC address, puts that in the packet, sends the packet to the router. The router strips off the Ethernet frame, says, yep, that's for me. That's how it knows it's destined for here. It strips off the trailer and analyzes the IP packet. So here's the decapsulated packet going into the router, looking for that 2 address. The router looks at its routing table, looking for some prefix that matches 172.16.4.2 or 2.9, because that's where we're sending it to. So it finds 172.16.2.0/24, that matches. It then looks at where it's supposed to send that next. The next router is 172.16.4.2, and it's going out serial 000. The router then knows that it's going to send that packet, encapsulates with HDLC, and then sends it out the serial 000 interface. So it's actually up here. So it then travels across. Okay, so that's a lie. They've now changed. We're now going Ethernet between the routers as opposed to serial between the routers. But note, the 2 IP address still remains the same. The 2 MAC address in this scenario has now changed to the MAC address of R2. So it's sent out across. The router 2 then gets it. Okay, so we went back to serial again. I don't know. R2 then gets it and does the same thing. Strips off the headers, analyzes where the packet has to go via the IP routing table, puts headers back on, Ethernet headers in this case, to send back out on the network over here, where B then gets it, reads the MAC address that it would be to, which would be itself, brings that in, looks at the IP address, says that's for me, and then processes the packet. So looking at what routes exist in a device without doing any configuration other than the interface configuration, every device, every router is going to have connected routes for each interface. So it'll have one for gig 00, it'll have one for serial 000.001 in R1. R2 will have serial 001 and gig 00, whatever the IP addresses are. R3 will have serial 000's IP and gig 003 or 00 IP in its connected routing table. And by default, it can talk to anything that's connected. So without doing anything, if there was a device out here, if there could be a device out here, then the router would know how to talk to both those devices. So in this case, it knows how to talk to R2, it knows how to talk to R3, it knows how to talk to A without doing anything. What it doesn't know how to do is talk to anything on the other side of R2 or R3. So it doesn't know how to get to B or C. So when we look at our routing table and our IP addresses. So in this case, we have 3 IP addresses on 3 interfaces. And if we look at our routing table, that's all that's in here is our connected networks and our connected addresses. So the L basically is the assigned IP address for that interface. So if we look at the ARP table on the router, so in this case R2, we're going to see stuff connected to R2. 172.16.1, we're not going to see that for sure. They lie. This is routing table from R1, not R2. You only see ARP entries for local subnets, not for remote subnets. So this should be R1, not R2. So if I want to be able to route from, yeah, so Omega, they must have updated it in that. These slides are older. That's good. So in order for this router or anyone on the other side of this router to be able to talk to anyone over here, we have to tell it somehow how to get there. And to do that, we basically have to say, okay, anything destined for this network, 172.16.2.0/24, or with the subnet mask, we need to send it from R1 to R2, and then R2 can deal with it. So the route only ever deals with the next hop, right? The destination and the next hop is what we need to be able to do a route. So in this particular instance, if R1 wants to talk to these 2 subnets over here, we're going to need 2 static routes. One pointing to R2 to get to 172.16.2, and one pointing to R3 to get to 172.16.3. So let's look at what that looks like in our routing table. So we do a show IP route static, and we see that there's static entry. 172.16.2.0 is directly connected to serial 000. Note it says directly connected. That's because it's a serial interface, and on serial interfaces, I don't have to specify the remote side's IP. I can just say, send it out that serial link. Whereas the other one shows the IP address on 172.16.5.3, which is the IP address over here. And this would be the same if it was a gig Ethernet interface or any other type of Ethernet interface, as opposed to a serial interface. You can also do this on a serial interface because it does have an IP address here as well, up here as well, but I don't have to. On serial links, I can just send it out the interface. So here is an example of creating static host routes, which is not really true. This first one's not a host route. It's an actual network route. IP route 10.1.1.0, 255.255.255.0. Nope, not a host because 255 would be the host, to 10.2.2.2. So that means anytime this router sees anything destined for 10.1.1 anything, because of our subnet mask, it's going to send it to 10.2.2.2. That means it has a direct connection somehow to 10.2.2.2. It probably has an interface in the 10.2.2 network that it can then use to communicate to 10.2.2.2 directly. The second entry here is a individual host. So in this case, we're going to send the IP route to 10.1.1.9, 255.255.255.255, And we're sending that not to 10.222, but to 10.999. But isn't 10.119 included in the 10.110 subnet? What is the router going to do with that, do you think? Because this is, right? 10.119 is part of 10.110/24. So the router's got to somehow figure out which route is the best route, and it does that based on the prefix length. So in this case, the prefix length is 32 versus 24. So it's going to use this route first. So if it is 10.119, it's going to go to 10.999. If it's 10.11 anything else, it's going to go to 10.222. So in this particular instance here, we have two separate links, primary link and a backup link. The concept here is we could get to 172.16.2.0 via either of these links, right? I can go over the MPLS. I can go over the T1. The T1's a backup link, and it says we're statically setting the route. The primary link says we're using OSPF. So we're going to have to do some manipulation of this in order to get the routing to go properly. So here is an example of what the static route there would look like, going directly out the serial interface. So directly connected. And note that we have a route to this, 172.16.2, if I do a show IP route directly to that, that says we have a known static with a distance of 130. This distance becomes important. So distance of 130 is directly connected via serial 001. Now, this is supposed to be a backup link. So that means that in order for the router to choose this path, it needs a route, first of all, and it says it's using OSPF, which is a routing protocol, which we're going to talk about here shortly. It needs to have an administrative cost that's less than this 130. The distance would have to be less than 130 by default in order for the router to choose that path. And the reason that this works is because if we set this up with OSPF correctly, and this link goes down, then we lose all the OSPF routes, and the static route that's here for the backup link kicks in and gets entered into the actual routing table. So I can have multiple entries for any given destination with the same prefix length. I just have to differentiate which ones, so I know which ones will get put into the routing table. And the router does that based on this distance metric. And we'll see more of that when we look at OSPF. So the other thing that we can do is we can use default routes at these remote sites. So in this particular case, B1, we want to send all non-local packets to the core. Everything's going back here that's not local. So therefore, I don't need to create a bunch of routes here or run routing protocols. There's only one path. There's only one possible way to get there. I have to send it over to here. I just create one static route that's a default route. That'll look like this, IP route 0000, 0000 to serial 001. So anything you don't know where it is, send out to the core. And then note, if I do the show IP route, I see that static route. I also see this gateway of last resort 0000 to network 0000. That's letting the system know that I do have a default gateway. And then this is the actual default gateway, 0000/0. So if I want to permanently add static routes to the routing table, I can put the permanent command on the end. This just makes it so that they're always in the table as an option, right? And especially in this scenario, there is no other option, so I might as well make it a permanent route. The only way I can get anywhere else is via that connection. Set that as the permanent route. What this would actually end up doing is it would stop any other learned routes from being entered into the routing table if we did learn another route somehow. So here's an example of the routing table with OSPF. So I do a show IP route OSPF, learned routes. And in this case, I've learned a whole bunch of routes, 172.16.1.1. So this is 172.16.1.0 and 0000, which is my default gateway that I've also learned from OSPF. So note I have overlapping routes. I have 172.16.00/16/22. I have 172.16.1/24 and 11/32. How does the router know which routes to choose? It's always based on the longest prefix match. So if I get a packet that's destined for 172.16.0.10, the /22 is a longer match than the /16 prefix match, then it's going to use the 22 match versus the 16 match. When I run show IP route command, if I do run show IP route, I'm going to see all the routes that are installed in the router. That does not mean that those are the only options in the router. Those are the ones that are being currently utilized in the router by the router or potentially used in routing traffic. If I'm using routing protocols, it's very possible that there's backup routes that are not going to be installed in the router because the router isn't currently using them and doesn't need to currently use them. So the indicator at the beginning is telling you what type of route it is. So is it a connected route? Is it OSPF? Is it EIGRP? S for static? There's a bunch of others. Could be a BGP learned route or an ISIS learned route. The next thing is going to be our prefix subnet ID. So that's the thing we get at the end. We get our administrative distances and the metrics that go along with them. And this is used in order to calculate distances for routing purposes. And then we get where it's sending it to. So our next hop router. We get a timer. If it's a learned route, we're going to see a time in here of when it was first learned. So how long that route's been in the table. And then finally, the outgoing interface where we're actually sending it to. Any questions on the basics of routing? Oops, I didn't want to do that. I wanted to do this. So in a small network,